All right, great. It's a green laser too. Okay, thanks, Rainer, for the nice introduction, and thanks everybody for coming to hear me talk about what I do. Initially, I debated it whether I should give a title like this because everybody can understand every word of that title, whereas remaining, what I'm going to talk about is still pretty vague, and this one is very specific. And suddenly, then lots of terminology crawl into the title I have to explain. But nevertheless, at the end of the talk, I hope that this difference doesn't matter to every one of you. As Rainer said, this came out of work we did a couple of years ago, which came out in Nature Communications at the end of last year. Mostly done by my former student, then came back as my postdoc with my long-term collaborators, Alex Hager and Wick Haxton. And we got 15 minutes of fame. For me, because I came from China originally, some people found out that I did this thing without my knowledge. They drew a cartoon series about me. So this is what I look like in that cartoon. And the title for their cartoon series is called You Arose from the Death of Stars. So if you know this particular cartoon on the web, it's called Sheldon. And anyway, so that's the series they did about this work. Actually, it's a pretty good popular science. So I advertised for them as well. Well, as Rainer said, that my specialty is nuclear astrophysics. I think that to many people here, it's not a foreign word because you have a major facility here, the cyclotron facility, which does important work in that area. But I would like to try to be a bit more general because there are students in this audience may not have been very familiar with that field. What's nuclear astrophysics? Well, just like any science, especially the physical science, we really like to understand how the universe came together. But we wanted to understand that process leading up to the universe we observe today using very fundamental theory regarding the building blocks of matter and how these building blocks interact with each other to govern the various processes leading to the universe we observe today. And it's not some kind of empty kind of ideal. We really have concrete achievements to testify this is how we can be successful in this endeavor. So everybody have seen this chart of the fundamental particles, the quarks and the leptons, the neutrinos and the electrons are the leptons, and the U and D quarks are the basically make up the real matter in terms of the baryons, and how they interact with each other are the four fundamental interactions. And among the individual particles, mostly you're only worried about the electromagnetic, strong and weak interactions. But when we talk about the astrophysical objects, which are much, much large, like in Texas, everything is large, then you have to talk about the gravitational interactions. Now, why I say that we can claim some degree of success in this endeavor using this very reductionist approach to understand how the world came about. This is nicely exemplified by this effort, which is a few years ago. People tried to calculate the mass difference between the neutron and the proton, the most fundamental units in the nucleus. How can you use a theory about quarks to calculate this mass difference? It involves quantum chromodynamics and quantum electrodynamics, the most fundamental theory about the standard model we have today. And we know the measured difference between the neutron and proton is 1.293 megavolt. And that means that the neutron is slightly heavier than the proton. This theory can now calculate the difference within 20%, ab initio theory, okay? And with this kind of calculation, we put this input in our general understanding how the universe should work. When the Big Bang happened, at the beginning of the universe, everything is in thermal equilibrium. You ask how abundant the neutrons will be and the protons will be. Because neutron is slightly more massive, its abundance is smaller than the protons. So therefore, the universe started out with a proton-rich condition. And as the universe cools, neutrons and protons are no longer favored as a form of matter. These baryonic components will combine into nuclei. And mostly, the end result of that process, so-called the Big Bang nuclear synthesis, is to give us about 25% by mass of the baryonic matter ended up in helium-4. The rest of them, because we start out with a proton-rich condition, all ended up as hydrogen, which is just a proton. Okay? Because neutron is heavier than proton by that much, this is what the universe endowed every matter with this chemical composition at the beginning of this Big Bang nuclear synthesis. Now, the sun was formed about 4.6 billion years ago. From the modern cosmology we have, the universe is about 13.6, 13.7 billion years old also. So when the sun was formed, the universe was about 9 billion years old. Many things had happened in between. And one particular reflection of that many things happening is that the composition of baryonic matter changed quite a bit between the Big Bang debris and what the sun's materials was made of. We can look at the sun's photosphere and measure different kind of elemental abundances using spectroscopy, or we can study the meteorites brought back mostly from the moon missions, the Apollo project, look at it, those abundances as well. From those studies, both come to the same kind of conclusion. In the sun, 71% also the matter is still in hydrogen. Helium is about 27%. The rest of the periodic table, the astronomers are lazy. They don't call them individually anymore. They call them metals. All these guys only make up about 1.5% by mass. Although the number is small, but the variety is now very much the entire periodic table. Now, in between these two sets of numbers, what fundamental physics is at action? You say, well, I can see very easily proton is going down in mass. Helium-4 and other things are going up in mass. Well, baryon number is conserved. Roughly speaking, mass is conserved. So what is exactly happening is the following. Because beyond hydrogen, every nucleus must also have neutrons. And you are decreasing hydrogen, but making heavier nuclei more. The fundamental process is the universe has been turning protons into neutrons during those intervening years. That makes this solar composition possible. Well, if you know anything about fundamental interactions, if you want to change protons into neutrons, no other interaction can do it other than the weak interaction. Therefore, if you want to understand how this entire periodic table came about, you must understand weak interaction. And so I just indicate how do you turn protons into neutrons. I put them in quotes here because free protons obviously do not decay. This means that either the proton is inside the nucleus, somehow that it decays, it has enough energy to decay into another nucleus, but the proton switch into a neutron inside that nucleus, and in the process emit the neutrino, or you could move the neutrino to the other side, it becomes an anti-neutrino. The anti-neutrino obviously could actually, in principle, just talk to a free proton and turn into a neutron. So these weak interaction processes are the reason why you and I exist in the universe. So I talked about the strong and electromagnetic interaction and the weak interaction. What about this gravitational interaction? It's also very important because all these processes at the microscopic level, we already say that these are the things we understood. But the environment in which they actually undertake place is really in these astronomical objects. Basically, they are the stars. So after Big Bang, most of the nuclei in the periodic table are made in stars. The question then becomes, how do you make a star? Not everything can be a star, we know, because in the solar system, only sun is a star. The rest of the planets or meteorites, and what are the comets and things like that. They are not stars. So how to understand some object can become stars and some objects are just planets and other things? Well, it's a very simple application of understanding your knowledge about undergraduate physics, more or less. Basically, we think that the star initially started with a big gas cloud because the universe mostly is composed of these gas clouds, giant gas clouds. If you think about it, how do you go from a cloud to a shiny, compact object in the sky, like a star? Well, something has to contract it. How do you describe the contraction process? You say this cannot be a very fast process. Otherwise, we will see star forming all the time, and lots of things would be occurring in the sky. We don't see that. So this is a very slow process. In a slow process, you can approximate this collapse of the cloud in a quasi-static way. In a quasi-static way, you can assume some kind of quasi-static mechanical equilibrium. Some kind of a pressure support is balancing the gravity. And a simple way to understand this process is actually using energy arguments. Everybody taken some classical mechanics, you know something called the Virier theorem. Basically, in some hydrostatic equilibrium, the kinetic energy component of the system is comparable to the gravitational component of the same system. That's a criteria of quasi-hydrostatic equilibrium. So you say, for a proton inside this gas cloud, the gravitational potential energy is just this much for that proton. Associated with that proton, there's some certain of kinetic energy, which obviously provided the pressure to counter this gravitational collapse. One part of it initially is just the thermal motion. You have a certain temperature, that's some kinetic energy that gives you the pressure. But because we also considering this contraction process, when you contract, well, things become closer together. We know electrons are kind of exclusion principle particles. Basically, they are fermions. They do not like to get too close to each other. And this is essentially, basically, a fact of life. We know electrons are such particles. And when you squeeze electrons closer together enough, you essentially are putting them into little cubicles, like the graduate student offices, right? You know how it feels like when you put it into a cubicle. That's a psychological thing. But obviously, you also needed to consult with real physics, which is the uncertainty principle. When you put little particles in these well-defined cubicles, your position becomes well-defined. Well, if position is well-defined, your momentum becomes ill-defined. That means you have to sort of like climbing the walls and things like that, right? So the electrons are climbing walls in these cubicles. That means their energy contribution to the kinetic part of the pressure grows. So that then tells you the entire story about the collapse. You can work out how does the temperature really actually changes as a function of the shrinking radius of the cloud. You find out that actually initially it increases as the cloud shrinks, the temperature rises. But when the electrons in the cloud get so close, their degeneracy pressure takes over, then actually the temperature actually starts to decrease because you do not need the temperature to provide the pressure support anymore. Okay? So for any given mass cloud, there is always a maximum temperature you're going to ever reach during the collapsing process. And we know that you call a star because one, it's a symbol of light. That means it has to emit light, and energy conservation tells you something must be supplying that energy. Star is also a symbol of longevity, right? It's sort of always there lighting, for a long, long time. That means that this energy supply has to be, very long lasting. And we now know, obviously, the energy source is a nuclear fusion. Nuclear fusion do not take place at ordinary conditions because we never realize the fusion now on the Earth except in the explosive phase. The controlled fusion, we never realized yet. So you need a high temperature to overcome the Coulomb barrier between the nuclei in order to fuse them together. The temperature, the lowest possible, like what's going on in the sun, is about 1 kilovolts or 10 million degrees. So if you want to reach 10 million degrees temperature in the center of this collapsing cloud, how massive the star has to be, or the cloud has to be? It turns about 8% of the solar mass. The sun obviously qualifies as a star, so it's above that limit. But if your mass of the cloud initially is less than 8% of the mass of the sun, you will never become a star. You're just a rock, like a planet or something, all right? So we have this. Now you understand that the Earth, there's what do we call it, sitcom, called the third rock from the sun. So Earth is a rock. It's not a star. But we have lots of rock stars on the Earth, but they're not real stars because they don't shine. Okay. All right, now you understand the stars and all the four interactions basically that interplay. You really want to look at the environment, where these clouds are like. This is one of the picture with the stellar nursery, where all the stars, the light you see actually is the background stars. They're shining through the cloud. That's why the cloud silhouetted on this background that it has darker things. Each of these darker places are potentially a stellar nursery. And you can see that this structure is very complex. So let me give you some rough idea about the sizes and the masses of these units. So these clouds, that's a sort of a larger scale structure. The mass contained in it is about a few thousand solar mass or so. And the size of it is perhaps the tens of light years across. Okay? And within these clouds, there are denser clumps. These clumps typically contain about, say, like a few hundred solar mass or so. And their size about 10 times less, so you're looking at only light year across also. Whereas inside these dense clumps, there are even denser cores. These cores, the size comes down to the stellar mass scale. These are the initial nuggets which will essentially, accrete from the surrounding things or being triggered by some other factor start to collapse to form stars. And their size is even smaller, maybe a tenth of light years or so. Okay? Give you also some scale about the density. We are no longer talking about gram per cc because each 1 gram you have Avogadro numbers of particles, roughly speaking. We're now talking about densities of particles per cubic centimeter. In the general cloud, you have several hundred particles per cubic centimeter. Even in the denser part of the core, before they collapse into stars, you only have basically tens of thousands of particles per cubic centimeter. Very diluted stuff. But nevertheless, these are our stellar origin in the sense that when it's in the cloudy stage. The other important parameter I want to tell you is that like life, have taught us nothing lasts forever. If this is the birthplace for the stars, it doesn't stay that way forever. It has a life cycle. Typically, these giant molecular clouds will last between 15 to 40 million years or so before it's destroyed because it formed the stars, and these stars will output energy, make these clouds disperse. So that's part of that story. Now let's see that if I grab one of the core in these clouds, how does it form stars? This is a typical story. So that's a dark core before anything happened to it. Then by some trigger or by itself, some instability somehow happened inside this dark core. Gravity wins. It starts to make the thing contract. Now remember, when things change, the most interesting way to look at it is to look at anything do not change. Well, we know there are conservation laws for these mechanical processes. You think about energy conservation, which we already tried to figure out what the maximum temperature ever you get to in the core. And the other thing is about angular momentum. And any kind of object you look at around us, typically they are not really spherical. So this cloud initially is not spherically symmetric, so it has some kind of initial angular momentum. When you collapse, you have to remember angular momentum has to be conserved. So therefore, as you try to contract, that's the force of the gravity. You want to contract it. At the same time, you want to conserve angular momentum. The only way for you to do this is actually for you to spread out, right? It's very simple that you contract and you want to conserve angular momentum. So in this process, the initially roughly spherical cloud become a disk, okay? And so what happens in the disk is then, density is very high, and eventually you can imagine that the debris starts to attract around their surroundings, make a core of things, and these debris gather further by accretion, you make planets, okay? The central object essentially has the most mass of the original cloud, becomes the central star. And these debris in the disk, because they gather the stuff in the disk, they become planets. And that explains why in the solar system, all the planets actually more or less lie in the same plane, and also they always orbit the sun in the same direction, in the sense of direction. This is basically conservation of angular momentum, more or less. And you can also see that as this process is happening, angular momentum conservation basically spread things out, and things also collapsing in the middle. You can imagine that in the central region, along the axis of the rotation, things get quite evacuated because centrifugal force, right? So any kind of energy you're able to dump into that evacuated region will be able to push out the material with high efficiency. That's why you see jets coming out of these things. So these jets are essentially the cleaner of this formation process. Afterwards, all the debris essentially gets, blown out in these two directions. You have now a well-designed planetary system with a central star and planets orbiting it around in the disk fashion. So this is how we think a typical stellar system is formed. Now, I wanted to come back to the issue about the triggering. How do you know these things can always happen with high frequency? One of the facts we know is that, as I say, the molecular clouds, the nursery, last about 15 to 40 million years or so. And when you form stars, obviously, you do not form just one star, because initially the mass is several thousand solar mass. You perhaps form 10 solar mass, 100 solar mass of total number of stars, okay? And some of these stars will be massive stars. And as I will tell you a bit later, massive stars become supernova. Supernova explodes. When they explode, that time scale is not very long, because massive stars live much shorter lifetimes. For a 10 solar mass star, lifetime is about 20 million years or so, okay? If you go higher, 20, 30 solar mass, their lifetime is 10 million years or less. So it's much less than the lifetime of the molecular clouds. So while the molecular clouds are still able to facilitate the formation of newer stars, some of the earlier formed supernova would have blown off. And their explosion would send out shock waves. These shock waves then will compress these cores and start the collapsing process for formation of new stars. And this, again, is not some wishful thinking. And you can be very poetic. These things are happening, blah, blah. And it's a very nice thing. But we actually have to model it. And the group led by Alan Boss actually has done a series of these nice calculations to show how actually a shock wave can trigger the collapse of a cloud and make at least a protostellar system. Okay, so what's shown here is a cross-section. So you essentially are cutting through center of this gas sphere, basically the original cloud. The coloring, obviously, red means higher density, green means lower density. And so initially the cloud, because I said that the angular momentum is slowly rotating and the axis is like this. And let's say that you have a shock wave represented by this horizontal bar, which is now going in the direction of the rotational axis. It's going to compress it. So the simulation then goes. See what's going to happen. What's going to happen, you see, is that the shock wave will immediately wrap around this smaller spherical cloud, compressed like this, okay? And at the same time, you see that there is an interaction between the shock front and this gas cloud. You can see these lots of inhomogeneities going on here. And these inhomogeneities do two things. One is that it mixes the material brought by the shock wave into this cloud. Okay, so bring new material from the supernova into the cloud. The other thing it does is that it injects angular momentum, because again, this process is very asymmetric. So you can inject angular momentum in this thing as well. Eventually, by about, say, 0.08 million years after the contact with this cloud, you see that this original spherical cloud already deformed into a disk. This is essentially where this planetary system, including the central star, will be formed eventually in this way. Okay? So there are some correct criteria for this process to complete, like I have described. First of all, the shock velocity cannot be very large. If it's too large, instead of compressing it, it just rips the cloud apart. Then you don't form stars, you destroy the stellar nursery, right? And then if it's too small velocity, then it doesn't basically perturb this thing, does not trigger the collapse. So you have to be in this range. When the shock hits this cloud, the velocity has to be between 20 to 40 kilometers per second. So that sets the size. So that if I want to think about the solar system was triggered by some supernova explosion, that supernova is not arbitrary. It has to be at the right distance. When it comes to me, the velocity has to be in this range. Okay, so it's relatively nearby. Okay, and then we do know there is then a connection. One is that the causal connection in time. If the solar system formation was triggered by a supernova, it has to be within a reasonably short amount of time. The two events cannot be too displaced in time. Then the evidence of it is that because the shock wave will inject supernova material into this protosolar cloud, I should be able to search for those clues. what did that supernova bring into the solar system so that I can demonstrate this is actually a possibility. Okay? So that's essentially a sketch of what I'm going to detail later. All right, so let me summarize what I have just told you in generality, what exactly happens in a cloud and how does it provide the environment for forming stars. So you can think about it as many cycles. One cycle is the gas, which provided the material for forming stars. I said that you form a molecular cloud. It collapses in the core to make stars, and the stars come in different varieties. They evolve. Some of them become supernova, and that input energy into the cloud eventually destroys the cloud. But these clouds get scattered. Eventually, under gravity, they will gather again, and they cool down, become molecular clouds again, form new stars. This is the gas cycle. This is how the birth environment of any star is like. It does not just come from one cloud. The cloud has gone through these cycles many times. The other one is the players in this game. One is provide energy input to disturb these clouds, and also going supernova, providing shockwave to compress these clouds to form stars. The third is that these same kind of supernova may also provide elements to the newly formed stars. But just like human beings, we come in different sizes and different kind of personalities. That makes the world very interesting. So this story about how to understand what kind of elements supernova provided to a star is also very interesting. It depends on their characteristics as well. But unlike human beings, we are much more complex to analyze. That's why I go into physics rather than psychology or other things. But this one is simpler. In a sense, you can think about it as a, this is a 23andMe, right? 23 chromosomes, and it's supposedly your life ahead of you has already been mapped out. This is similar things. This is like a 23andMe for the stars. So the stars are characterized by their mass. That's one of the most important parameters for their genetics, okay? I already told you, if the mass is less than 8% of the solar mass, you'll never become a star. You're done, okay? You're excluded from the club. Now, what's shown here is the vertical axis is the central temperature of a star at any given time, and horizontal axis is the central density. You can imagine that, as I said, that as the core collapses, the density will increase. As the density increases this direction, you can imagine the thing is shrinking. So the temperature initially rises, right? And it always hits a higher temperature, then afterwards it just drops. So if you never reach the temperature enough to burn hydrogen, you never qualify as a star. So these guys are excluded. Now, if your mass is above 8% of a solar mass, but still less than half a solar mass, you will be able to ignite hydrogen burning. But after you burn hydrogen to helium in the center, you ran out of fuel. If you want to ignite helium burning, your mass has to be above about half a solar mass or so. So those guys between 8% and a half solar mass will end up basically only have the product of hydrogen burning, which is helium in the core. They become helium dwarf, and they sort of like are done with that. Only stars above half a solar mass, you are able to contract and raise the temperature enough to burn helium in the center. And after helium is ignited, you will be able to produce carbon and oxygen. And those guys, then if their mass is less than about, let's say, 7 solar mass or so, well, you stop there. You cannot process carbon and oxygen because that also requires higher temperature. And if you are below, say, 7 solar mass or so, no matter how hard you're going to contract, you will never reach those temperatures to burn the carbon and hydrogen. So those guys ended up as carbon-oxygen white dwarfs, okay? Now, you go further. You say that if I'm now between 7 and 8 solar mass or so, that's become delicate. You might be able to barely burn carbon, but after that, immediately you sort of encounter degeneracy. So temperature is no longer be able to sustain a lot of the things, the burning anymore. So you end up with something called oxygen, neon, magnesium white dwarfs. And there is a very interesting range between 8 and 9 solar masses. You again will be able to trigger carbon burning. But when you burn it the density of the core rises to so high. You already know the electrons are now degenerate, but degeneracy could be so high, electron also become relativistic. When it becomes relativistic, its energy is like 10, MeV range, okay? You have nuclei like oxygen, neon, magnesium sitting around. And the electron degeneracy is providing the pressure support against the gravity. But if the electrons are energetic enough, they're going to capture onto these nuclei. Then you deprive the core of degeneracy support. The core starts to collapse. And that is initiation of one of the kind of core collapse supernova, right? And if you're outside this range, between, say, 9 and 100 solar mass or so, you will be able to smoothly burn everything all the way up to the iron group. And everybody knows that iron group is the most tightly bound nucleus. You can't possibly get energy by, processing these things further. But also at that time, the diagram, for these stars, the conditions in terms of temperature density at that stage landed in a part of the phase space on this temperature density diagram. If you use thermodynamics to understand it, the favored form of the matter at those conditions are no longer the iron group, but more like alpha particles in the free nucleons. So you go through some sort of almost like a phase transition, that you are making iron, but the conditions do not favor you. So the iron dissociates into alpha particles and free nucleons. And that process costs a lot of energy. You again rob the core of the pressure support. And these guys, again, collapses, give another kind of core collapse supernova. So this is how we know that these different mass stars will end up in different ways. And most important to me is I want to focus on these core collapse supernova kind. Between 8 and 9 solar mass, you collapse because you reach at the end point of the evolution, the electron start to capture on the nuclei, rob the core of the degeneracy pressure, and you collapse. The other kind is between 9 and 100 solar mass. You process all the way to iron nuclei. These nuclei are not favored by those thermodynamic conditions. They get dissociated into neutrons and the protons and the alpha particles. You lose energy that way, and you also collapse. And they become supernova. So basically what I'm telling you is that stars, when they formed from their nursery, they have two broad paths ahead of them. The average stars like our sun, they mostly do not become supernova. They basically end up with some kind of white dwarf, and mostly a carbon-oxygen kind. And then the envelope will be lost by lots of instability along the way. And so the white dwarf will be bared to you. And if you understand, poetically, what's a white dwarf? Well, it's Snow White and the Seven Dwarfs, sort of. Basically, dwarf means it's small. The reason is very simple. In order to burn things, you need to contract. When you contract to the last minute in order to burn helium into carbon and oxygen, obviously you have to contract a lot. That's why you become a dwarf. Why it's white? White is because it's hot. You contract to raise the temperature. So that's white dwarf. Okay? And so that's essentially your end of your life if you are in a singular configuration. Average star like our sun. Now, if you are more massive, like more than 8 solar mass, maybe 10 solar mass, even further, then you can go through all the stages of evolution of the burning in the center, and you eventually become a supernova. And you leave it behind either a neutron star or a black hole. And these are called a core collapse supernova. And the envelope is disrupted in a supernova explosion. And again, I like to make an analogy with the human society. Well, we don't like to be lonely. Okay, we always make friends. Eventually make families and things like that. So stars do things like that too. No stars always in a singular configuration. Actually, half of the stellar system are in binaries, maybe even more. So if you have actually two stars formed together, one of them evolves slightly earlier, become a white dwarf, and the slightly less massive guy is still evolving. This white dwarf actually is able to grab mass from the other companion, and when the mass is piled up on the white dwarf enough, push over some limit, which say that under this degeneracy pressure by the electrons, you're no longer able to support this mass anymore, then this white dwarf basically can just trigger some instability again. And because the white dwarf is still fresh off these nuclear fuels like carbon and oxygen, they basically get burned up and make a very big explosion. That's called a type 1a supernova. And this type 1a supernova, I remind you, basically is behind this Nobel Prize in 2011 because we know pretty well what is the light curve, powered by, because you are burning high carbon and oxygen into ion group. That's the energy release. You know how much luminosity pretty much is, released in this process. Then you observe its brightness on the Earth. From that, you can essentially calculate the distance. And you can measure its redshift. And the distance redshift measurement can test a cosmological model, because any cosmological model can tell you if you add this redshift, how far away you should be. And from that, we found out that the universe actually is expanding. Okay? And for the nuclear synthesis-wise, I just want you to remember, most of these type 1a supernova, they are the contributors of the ion group nuclei. More than half of the ion group nuclei in the solar system actually were made by these type 1a supernovas. Now, what about those massive guys? If you leave a neutron star in a singular configuration, that's it. It just rotates by itself and it just lives its lonely life away. But if you happen to have a neutron star, with another neutron star, or a neutron star with a black hole, or two black holes, formed in this binary situation, we now know that the biggest exciting thing is that LIGO has detected the gravitational wave from these two black holes circulating around each other in the binary, right? That's very exciting. We know that the first real detection of gravitational wave come from these binary systems. For nuclear synthesis, these things are also very interesting, because imagine when you have these systems, at least one of them is a neutron star, so it's full of neutrons. And as they sort of like go around each other, they emit the gravitational waves. So gravitation will carry away energy from the system. So the system will getting closer and closer because they fall deeper into the gravitational potential. Now, you remember that the gravitational force also acted in a very interesting way, because neutron stars are very strong gravitational sources. And initially, when they're far apart, you can regard them as essentially point particles. But when they get very close, well, this side of the neutron star is closer to the other guy. The other side of the neutron star is further away. So there will be a tidal force. Just like how the moon raises tides on the Earth, the other neutron star or other black hole is raising tides on this neutron star. As a result of the tidal force, one of these neutron stars will be ripped apart. And the neutrons dispersed in this process then supplies the basic material to build up a very interesting nuclear synthesis, basically things all the way up to uranium and thorium. This, we think, is the best theory now for us to understand how uranium and thorium came from. It's coming from these binary neutron stars. Okay, so basically let me summarize what I've told you. So in the stellar nursery, you think about the universe, in terms of how it functions as making these elements as a factor of elements. It's almost like a computer program. So you have this clouds making these stars, and depending on your mass, you either end up, with white dwarf, or you blow up as supernova, leaving behind as a neutron star and the black holes. And whatever the material you ejected at the end of your life returns to the stellar nursery and starts the next generation of stars. Okay? You go through the cycle, the loop, many times. Eventually, the solar system will appear. And we are just lucky that we happen to be in this system and allow us to exist. Life sprung up from one of the planets in the system. And I also remind you that this graveyard of stellar evolution, consisting of white dwarfs, neutron stars, and black holes, it's not a pure graveyard. If these guys happen to be binaries, these gravestones can be resurrected, essentially. The tombs can be resurrected into these interesting ways of making nuclear synthesis. Type 1a supernova involving the burning away of this white dwarf gives us ion group, and the neutron star merges, ejects some of this material, gives us uranium and thorium, essentially. This is how this entire periodic table in the solar system was printed in a way in this factory. Okay, So now let me focus on what exactly happened in the solar neighborhood. We know this picture happens more or less everywhere in the universe. What exactly happened in the solar neighborhood? Let's do some simple calculations. How many supernovae have to be occurring over the 9 billion years during Big Bang nucleosynthesis and the solar system formation? That's 9 billion years. How many supernovae took place? And what did they do? So the supernova rate in the galactic disk, typically is about once every 30 years or so, it's rough estimate, okay? The amount of gas, which essentially is available for forming stars, when some of them will become supernova, is about 10 to the 10 solar masses. But each supernova, once it's evolved to its extreme limit, how much mass it can influence in its neighborhood? It's about 30,000 solar masses. So if I want to stand at an average point in the galactic disk, I want to ask how often I would receive contributions from a supernova. I would just do this very simple scaling. The mixing mass by each supernova is 30,000 solar mass, and the total amount of gas in the disk is about 10 to the 10 solar mass. The total rate over this total mass of gas is once every 30 years. You work it out at average point in the galaxy, in the disk, once every 10 million years, you would expect one supernova to sweep you by. Okay? Now, I said 9 billion years interspersed between the Big Bang and the solar system formation. So altogether, we would have had 900 supernova in this neighborhood. Those 900 supernova are the contributors to the entire periodic table, more or less, of the solar system. It's not one supernova, it's this many, close to almost 1,000, right? Now, what's so special about the last supernova? Because I want to understand the trigger. Most of these supernovae happened long ago, 9 billion years, right? Time. I don't feel interested in them because they are not timely correlated with the solar system formation event. They're just preparing the nursery. Okay, the preparing the nursery, that's all. I want to understand the last supernova, how special is it? You imagine that we now can find pieces of meteorites, okay, falling to the Earth or brought back from the moon. You analyze their composition. The major elements like magnesium, silicon, calcium, iron, you find out the relative abundance distributions. They're very uniform. No matter where you find these meteorites, the ratios of these elements and their isotopes are very uniform. They are better than 1% precision. You can say that these things are exactly identical. So that tells you this overall composition of these elements come from a grand mixing process. These 900 supernova, most of them are essentially happened long ago, and they're stirring up the gas in the nursery, and so you have a very uniform composition in that nursery. Except the last supernova is special, because the last supernova triggered the supernova formation, the solar system formation. It does not have time to mix all its components throughout this nursery, right? It does not do that anymore. So if you want this guy to be the trigger, you also have to place a constraint on it. Do no evil. I already prepared a very uniform background. If you are a special guy coming with an abundance pattern which is very different from the grand average from these past 900 supernova, you'll stand out. But I don't see it in the data. So that guy cannot be any kind of supernova. It has to be special. Okay? So I just showed you that this is a mixing process. When you trigger this guy, the supernova debris gets mixed throughout this cloud, but in different parts of the solar system, they will distribute different matters, okay? The only way for you not to screw up this uniform pattern of the stable elements is that you didn't contribute a lot of it. Just minuscule, you're just salting the thing a little bit, but you don't taste the salt if you put too little of it in it. And I just showed you, these are the real calculations. This is the supernova progenitor's mass from 12 solar mass to 30 solar mass. As you can see, for these major elements like carbon, oxygen, magnesium, silicon, calcium, and iron, their relative patterns are very different as a function of the mass. And also, if you normalize this thing to the lowest mass model here, 12 solar mass, typically the absolute amount of production increases dramatically, sometimes by a factor of several factor of 10 as you go to higher masses. So you know that in order to do no evil, not screw up this uniform distribution of the relative abundance patterns, you cannot allow these massive supernova to be the trigger. Otherwise, you would have introduced inhomogeneity in these abundance patterns. And the lower you go, the easier you can satisfy that constraint. The other thing is also identify any radioactivities. I say that I want the trigger to be identified, with some evidence. One of the interesting evidence would be a causal connection. The causal connection is that this trigger have to happen with a relatively short amount of time before the solar system formation, let's say a few million years or so. We do find that there are radioactive nuclei in the early solar system. We found out about these guys' existence from the decay products in the meteorites. All these nuclei are listed here: beryllium-10, calcium-41, manganese 53, iron 60, and the palladium-107. Their lifetime is afford a few million years or so. They are existing in the early solar system. So something must have delivered it to the solar system. And most likely, it has to be a supernova. Again, you cannot screw up this uniform pattern in the stable guys. Also, you cannot introduce too much of this radioactivity either, because we have absolute amount measured already about how much of it you can inject into the solar system in terms of these guys. You can see, again, as a function of the mass, as you go to heavier masses, you produce a lot of these radioactivities. So both the stable elements and the radioactivity's absolute amount tells us the triggering supernova could not have been a very massive one, all right? It's likely to be a low mass one. Now, let me just tell you how we actually have these very different kind of a nuclear synthesis because of different progenitor masses. This shows you the structure at the point of collapse. This is the density. This is the mass enclosed up to a certain radius. Okay, let's say that if you are enclosing about 1.45 solar mass or so, it's over here, and at the edge of that enclosure, the density is 10 to the 4 gram per cc for this particular supernova. And that supernova mass is only 9.2 solar masses. And likewise, you can see that if you go to heavier solar masses, the density decreases much slower, whereas the smaller supernova, they decrease very fast. And when the shock wave generated from the center of the supernova propagates through these envelopes, you have very little material to be processed for low mass supernova, whereas these heavy progenitors have a lot of material to be processed by the supernova. That's the reason why the yields increase very dramatically as you go to heavy masses. Okay? So I wanted to say that the evidence is nice, so you are just luring out one class of supernova. Heavy mass don't do a good job about triggering because the constraints of a stable nucleus abundance pattern, and you cannot overproduce the radioactivity stuff. But what about any positive thing? Not just that you do not do no evil. Anything good you can do with a low mass supernova? Well, we can find such a nice feature about this low mass supernova. Let's look at the sky, 12 solar mass. You find out all these radioactivity, typically their yields, production amount will increase dramatically as the mass of the supernova increases, with one exception, which is beryllium-10. Beryllium-10, as you go across this mass range, the production doesn't change within a factor of 2. Okay, that's very nice. And you know that the beryllium-10 is not changing very much. That means its relative importance is getting more and more as you go towards the lower mass. In terms of radioactivity, for the heavy mass guys, the most important radioactivity are these guys, which is very high yields. Beryllium is not very important. But when you go to lower masses, beryllium essentially gets equally important with the rest of them. So you see that beryllium look like a very nice signature. And how do we find the beryllium-10 in the early solar system? And how do we make them in the supernova? First of all, supernova happens when the central part of the core collapses into a neutron star, as I said. In the process, lots of gravitational energy is released because the neutron star is much more compact configuration. It's sunk into a much deeper gravitational potential. And all that energy has to be released somehow. Now, at those high densities and high temperatures encountered during this collapsing process, you think about how do you get rid of energy, you think about the microscopic processes. The most weak interaction will allow you to get rid of that energy in the most efficient way. Here again, the weak interaction helps you. So that energy in forming the neutron star mostly comes out in neutrinos because neutrino can escape from the dense environment in the easiest way. Now, these neutrinos, when they escape, they came away with energies typically of 10 to 20 MeV or so, as verified by detection from neutrinos we see from supernova 1987A in the Large Magellanic Cloud. And some of these guys, eventually, when they go through the envelope, will have a chance to interact with some of the nuclei there. You don't need to do a lot. And let's say that in the outer layer of the supernova, there is some carbon-12 sitting there. And neutrinos coming with 10, 20 MeV, you interact with it. You highly excite the carbon nucleus. And this carbon nucleus is not likely to stay like that. It's like, you become too high, drinking lots of wine, you become agitated, and you're going to throw up. So this guy threw up 2 protons, and so ended up remaining with the beryllium-10. Beryllium-10 is the guy which you want. And so now you know I can make beryllium-10 in the supernova. And I found beryllium-10 in the solar system. This is how exactly then I can explain it. Okay? All right. So let's put the whole story together. If you just explain 1 beryllium-10, it's not much. Okay, you say that you have one observational data point, and you have a model. Say you made this beryllium-10 in the supernova, they match, so what? Luckily, we have more than one radioactive nuclei. You have calcium-41, you have beryllium-10, you have palladium-107. We really only have 2 parameters in the model to explain this trigger. You have to say, once the supernova exploded, how long has it to wait before the solar system was triggered to form, and therefore the meteorites would form that incorporate whatever the supernova has dumped into the solar system. So that's a time delay. The other one is that the supernova, as it expands, it becomes very large, whereas the cloud, as you remember, initially size only about 1/10 of a light year across. So the supernova shockwave would intercept only part of the shockwave will intercept that. So what fraction of the original supernova production gets injected into the solar system is an unknown at this point. So we say that fraction is also a parameter. But with this parameter, what fraction of the supernova ejecta gets incorporated into the solar cloud? How long did it take for the supernova to, send the material over and it gets solidified into these meteorites? That's a time scale. These 2 parameters, once you have them, it has to apply to all the radioactivity you are sending to the solar system. With 2 parameters, we have 3 equations, basically 3 unknowns. Normally, you cannot do that. Well, in our case, you can do it. That tests you that you really have some kind of nice way to explain these 3 radioactivity. So as you can see here, we can not only just explain beryllium-10, you can also explain calcium-41 and palladium-107. Okay, I would end with some caveats. It's not a rosy story that everything we talked about is jolly fine, and there are problems which we cannot do justification yet. Okay, but we think that it's solvable. One is that manganese 53 I showed you. It's also detected in the early solar system. Same thing with iron 60, and the model we have here produced too much of it. Although it does not produce as much as the higher mass models. We are the lowest, I always say least worst in terms of overproduction of manganese 53 and iron 60. But this is actually a solvable problem in the sense that if you look at it, where most of the manganese 53 and iron 60 are being produced, so this color is over here, so the purple curve and this cyan curve over here. Most of them are produced very close to the core of the supernova. That's the least certain region which we can calculate in terms of supernova modeling at this point, because as you know, that we succeeded in exploding supernova only in relatively few cases. Basically, spherically symmetric modeling is routinely done. But if you try to include any realistic consideration, maybe that there were initially rotation of the star and there were more complicated hydrodynamic process in the process, the most thing it will affect is how this inner part of the ejecta will be processed by the shockwave. And so we think that with better modeling, this problem may be even solved as well. So let me sort of summarize and finish. So I have told you that by constraining, from the meteoric data, telling us the major stable elements like magnesium, silicon, calcium, iron, they come in uniform pattern everywhere in the solar system. We say that you can't possibly, trigger this formation by a heavy mass sky because it will dump a lot of the things and ruin this uniform pattern. And also, likewise, you can't possibly allow that massive trigger because it will produce even more manganese 53 and iron 60. This leaves us as an option. Basically, low mass cold collapse supernova still can be the trigger. And the real good evidence pointing to it right now we have is that it can automatically explain beryllium-10, calcium-41, and palladium-107. Okay, but we need more sophisticated modeling about supernova in order to solve this problem. Even in this case, we are overproducing quite a bit about manganese 53 and iron 60. Okay, and obviously there are lots of things to be done in the future. And I would highlight actually even with the beryllium-10 story, you see that it's a very nice nuclear reaction. Neutrino excite carbon-12, and there's a channel that for it to spit out the 2 protons and leave you behind with a beryllium-10. We calculated this thing with theory, and we think that the confidence level is at a factor of 2-ish. Okay, if you want to improve this nice story, and maybe that say that it's not a factor of 2, we would like to understand it, maybe within 20% or something, then we need a lot of nuclear input. In this case, perhaps we cannot rely on calculation only. We really would like somebody to go out and help us by make a measurement. Thank you. Very good. Trigger. All right. Okay. So one thing I can say that if from the point of view of the beryllium-10, you can't possibly make it in type 1A. Because typically how people would like to make beryllium-10, because it's very fragile. And so you can't typically allow this thing sitting in a stellar environment for long because it burns up by proton capture. At millions of degrees, it just burns up. And so typically people talk about is you use cosmic rays. You have carbon-12 sitting out in the interstellar medium, which is a very cold place. And then you have cosmic rays just bombard it. You also just spit out the 2 protons, so you get this thing. That's easy, right? Except then it's pretty arbitrary. So you have to tune your cosmic ray flux in this way and that way. So in our case, we achieved it because the cold place you found is the outer layer of the type 2 supernova, and where it abundantly have carbon sitting there. And then you use the energetic particles from the center of the supernova generated by the formation of a neutron star, which is the neutrinos. These guys then use the energy to knock out the particles. So this is how it's achieved. Then you can calculate this yield, as I say, with a factor of 2 or so. And then you fit the overall pattern, which then say that this kind of a supernova explanation using the core collapse kind can explain this set of data. If you rely on beryllium-10 coming from a stellar source, this is, so far as I can see, the only way you can do it. So it's type 1A because it does not make beryllium-10, you will not be able to do it. And otherwise, most of the radioactivity you will produce in type 1A is typically in a dominant, obviously, nickel 56 and also other iron group. But it does not come along with, say, calcium 41, palladium 107, because these are really outside of the range of the production for that model. So from radioactivity, I would say that it would not do so. The third thing I would say is, again, about the uniformity. Remember that no matter what dumped in the last bit of material before the sun was formed, you cannot ruin the overall abundance pattern, which is set up in such a uniform way within 1%. We know type 1A dumps out about, say, like 0.7 solar mass of iron, right? And if you go there, and then no matter how you want to dilute it, it's very hard to satisfy that constraint. And this can be made a lot more quantitative. Remember that I also say that you have to have the supernova shockwave hitting the cloud when its velocity is about 20 to 40 kilometers per second. Now you can just work out backward. If I want to dump 0.7 solar mass of iron without affecting the uniformity of the pattern, at the same time, I also want to reach 20 to 40 kilometers per second when I hit the cloud. Can you make a type 1a supernova in that order? If you cannot, then there's no way that from that also. Many arguments you can say that basically will not be able to do that. Yep. 9 billion years. It cannot. It has to be the last one. Remember that no matter what, at any average point in a galaxy, you always are cycling through these molecular clouds, star formation, and the dispersal of the clouds, gathering again. This is what's happening. What's more interesting is that it's better to play the movie backward. You say that I know when the sun was formed, okay, it has some meteorites formed at the same time. And now I look at the meteorites. I found that there's some peculiarity in it. This peculiarity can only be explained because when it was formed, it incorporated some live radioactive nuclei. And those guys' lifetime is only a few million years. You say, how did they get there? Okay, it got to be a very recent event dumped into that short-lived radioactive nuclei when the solar system was collapsing. That's the only causal thing you can explain. If it's too far early, let's say that you did this 10 million years earlier, well, any kind of radioactivity you have produced, many epochs later, is already gone. Even though you're triggering some formation of the stars in the neighborhood, that's not our solar system. It's just unrelated to the particular stars we wanted to understand with these meteoritic data. Yeah, three things. That's exactly. This is delta is the time basically between the supernova explosion and the time the radioactivity gets incorporated into the meteorites. That's a time delay. Okay, so it basically says that it's about with a million years or so this happened. Yep. It's a very good question. I should actually expand on that as well. So you see this one, when Alan Boss group did this calculation, they obviously have to set up, because it's a numerical experiment, you have to give it an initial configuration. This is one set of experiments it did. So the shockwave comes in, propagates along the direction of the rotational axis. And in this case, obviously, you can see that the disk is formed perpendicular to the rotation axis in the end. But this doesn't have to be the case. He did another set of calculation where the shockwave goes sideways. And what's interesting here is that the disk orientation becomes random. I mentioned it when I was explaining here, what the shockwave does, in addition to compressing the cloud to collapse, it also did two things. One is the injection of this material from the supernova. The other one is also injected angular momentum. So the final disk orientation is not determined by its initial angular momentum anymore. Because of the shock injection, its angular momentum may very well determine the final orientation of the disk. So this is the conclusion. It has to be. Yeah, sure. We know that. Yeah, very good. So you work out the systematics. They say that I needed to come to this cloud at the velocity of 20 to 40 kilometers or so. And using the density of a typical environment, you find out that the supernova initially had to happen perhaps, say several light years away. And in order to do that, you can do this thing, right? And also, you remember that we also needed to explain this overall injection. You do see this much radioactivity. You know what fraction of the 4 pi you are covering, when you hit the cloud, right? That's also needed. And the bad thing about it is that because it happened too many years ago. Remember, the sun was formed 4.6 billion years ago. Okay, that's a long time ago. So any kind of supernova remnant, which triggered this formation, would have long lost its trace. Right? You won't be able to trace it anymore. Many things happening in this thing. And if you left behind a neutron star or black hole, whatever that is, most likely if it's a low mass supernova, it has to be a neutron star. Any neutron star typically was born with a kick. So it typically moves at the velocities of, say, 30 kilometers per second or so. 30 kilometers per second multiplied 4.6 billion years is way away from us. So you won't be able to find anything. So radioactivity and nucleosynthetic signatures are the only ways we are able to infer any kind of connection with this particular supernova.
Last question.
Correct. Yep. Mm-hmm. Lago, right. Right. That's a very good question. I think that then we have to step back a little bit, right? So let's say that now it's harder than again to find the real supernova who did this thing, whatever it's remain, in terms of the kinematics, other things perhaps it's already gone. The only thing you would look for is the chemical signature, right? So if you are saying that, if we are thinking about this, contemplate this scenario that the sun was formed together with several other stars as well, and the supernova, because obviously it will involve influence a much larger region than just the solar cloud, you would look for that signature. We know that in the sun, the chemical composition is extremely uniform. So that has to be a criteria. Then you say that, do those kind of a moving group stars also do not have this, weird kind of irregularity? It also has a regular. It doesn't prove that it has to be like that, but at least it rule out the possibility that, somehow it's much more complex. Let's say that if these moving group of stars we think are formed together with the sun has irregular pattern, then makes the scenario very hard to be self-consistent, because we say that, in order to explain the sun without these irregularities, you have to require the supernova not overproduce things. But if you see irregularity elsewhere, it's the same sort of thing, right? And how can you explain it? And so I would think that it's easier to falsify it if you see these irregularities in those contemporary stars formed at the same kind of a stage of the supernova explosion. But if you don't see them, it's also uniform. It's just consistent. You don't prove anything, but nevertheless, it's a worthwhile thing to find out ways to test these. First of all, find whether these evidence for these stars co-formed with the sun. Next is to really test their uniformity about their chemical composition. And from that point, at least we learn something.